Have you ever just stopped and looked around at, well, everything? The air you're breathing, the device you're watching this on, even your own body. Today, we're diving into the fundamental stuff that makes up all of it.
So think about it for a second. What could possibly connect a blazing star millions of miles away, a simple glass of water, and you? They seem like they're from completely different worlds, right? But believe it or not, they share one profound, fundamental thing.
And that's it. The answer is matter. Every single thing in the universe, from the tiniest speck of dust to the most massive galaxy, is all made of the same basic stuff. And if you can understand matter, you're on your way to understanding pretty much everything.
Now, this isn't some new question we just came up with. For thousands of years, brilliant minds have been trying to figure out what the world is actually made of. It's one of the oldest and most important quests in all of human history.
For a long, long time, there were basically two big ideas. One group of thinkers believed matter was continuous, like a solid block of wood. If you cut it, you just get smaller, but still solid pieces of wood. But the other group had a much wilder theory. What if everything was actually made of tiny, individual bits, more like a pile of sand?
Well, spoiler alert, the sand people were right. It turns out everything is made of unimaginably tiny particles. And once we figured that out, we started to uncover the secret, invisible rules that these particles play by, rules that literally shape our entire reality.
Okay, it's one thing to say that everything is made of particles, but how do we know? How can we be so sure that matter isn't just one solid, continuous thing? Well, the proof is actually something super simple, something you can even try at home.
Check this out. You take a glass of water and you stir in some salt. The salt just seems to vanish, right? But here's the crazy part. The water level doesn't really go up. So where did the salt go? It's still there. The tiny salt particles have just slipped into the empty spaces between the water particles. This could only happen if matter is made of separate little bits with gaps in between.
So that simple experiment proves the first rule in what we can call the particle playbook. Particles have space between them. But there are two more absolutely crucial rules. They're also in constant, non-stop motion, and they're always attracting each other. These three rules, they basically explain everything.
Let's dig into rule number 2, constant motion. Every single particle in the universe is always jiggling, vibrating, and moving around. They have what's called kinetic energy. Now, when you heat them up, you give them more energy, and they start moving way faster. It's why you can smell a hot pizza from across the room, but you have to get right up to a cold sandwich to smell it. Those aroma particles from the pizza are literally flying through the air faster.
And finally, rule number 3, particles attract each other. There's this little force that's always trying to pull them together. But here's the really important part. The strength of that attraction is different for different kinds of matter, and that difference is what makes a solid rock feel so different from liquid water.
This is a fantastic way to picture it. Imagine these dancers holding onto each other really tightly. It would be super hard to run through their line, right? That's kind of like a solid. The particles are holding on for dear life. But if they were just loosely touching fingertips, you could move through them much more easily. That's more like a liquid.
So when you put these three rules together, the space, the motion, and the attraction, what do you get? You get the three states of matter that make up our entire world: solids, liquids, and gases. It all makes sense now, doesn't it? In a solid, the attraction is super strong, and the particles have low energy, so they're locked in place. That's why solids have a definite shape. In a gas, the particles have tons of energy and weak attraction, so they just fly everywhere to fill whatever container they're in. And liquids? They're that fascinating, flowing middle ground.
Of course, these states aren't permanent. Matter can change. Ice melts into water, and water boils into steam. And all of these changes are really just a big battle between the particles' energy pushing them apart and their attraction pulling them together.
This brings us to a really cool and kind of weird puzzle. So imagine you're heating up some ice with a thermometer in it. The temperature climbs up to 0 degrees Celsius, and then it just gets stuck. It stays at exactly 0 until every last bit of ice has melted. But you're still adding heat. So where's all that energy going?
The answer is a concept called latent heat. The word latent actually means hidden. So this is hidden heat. It's not making the particles jiggle faster, which is what temperature measures. Instead, that energy is doing a different job. It's being used to break the strong bonds holding the particles together in their icy structure.
And this shows that effect perfectly. You can see we're pumping in more and more energy, but the temperature just flatlines. It will not budge one bit until that whole state change is complete. All that hidden energy is busy breaking the particles free.
All right, so solid to liquid to gas is the standard path. But what about a shortcut? Is it possible for a solid to just poof, turn straight into a gas, completely skipping that whole messy liquid phase?
Oh, absolutely. And it has a really cool name for it, too. It's called sublimation. It's that direct jump from a solid right into a gas.
And the classic example you've probably seen is dry ice. That's just solid carbon dioxide. It doesn't melt into a puddle of liquid CO2. It just turns into that spooky, rolling cloud of gas you see at concerts or on Halloween. That's sublimation right there.
Okay, let's bring all this science right back home to something you and I experience all the time. How do these particle rules explain the simple act of cooling down on a hot day?
The secret here is evaporation. Now, this is different from boiling, because evaporation can happen at pretty much any temperature. It's when just a few high-energy particles right at the surface of a liquid finally get enough of a kick to break free from their neighbors and escape into the air as a gas.
So why does that make you feel cool? Well, for those surface particles to escape, they have to steal a little bit of heat energy from whatever they're touching. When they're on your skin, they steal heat energy from you. And when your skin loses heat, your brain registers that as feeling cool. This is exactly how sweat works to cool you down.
And that leaves us with one last kind of mind-bending thought to chew on. We've established that everything, your hand, the table, the air, is just a collection of tiny particles with empty space in between. So if that's true, what does it really mean to touch something? Are any of those particles ever really truly making contact? Something to think about. Thanks for joining us.